In this video, we go back to an example that we looked at the very beginning of the course, Calculus 1. Used this example to motivate limits. There was some little people here, and they were going to jump off this cliff into the waterfall. I'm not advocating this. This is just an example of video that we had, and we're going to use it to illustrate a function with parameters. So we had here, we're repurposing this example from limits, and we're looking at now section 4.8, an example of rectilinear motion. Okay, and this video is specifically going to be talking about position and velocity. Okay, and we have all the tools that we need to do this problem and understand it. Okay, we've just come off of taking a bunch of derivatives, so using all the derivative shortcuts, and now we're going to put some of this into action. Okay, so we have here a function called y of t. It's a function with parameters. There is a g term for gravity. There is the initial velocity of the person that is jumping, and then there is the initial height that they are jumping from. Okay? And all these can be adjusted, the initial height and the initial velocity. Right? And we can't really do too much about gravity at the surface of the Earth, so we're just going to assume gravity is a constant, okay, and not a parameter. And what we are seeing in this problem is at different values of time, okay, the function y of t tells us about the position of the person who is jumping. So at time t equals 0, we can see that their position is about 60 feet. This cliff is about 60 feet tall. Okay, and then as the person continues to fall, maybe 1 second into their flight plan, t is equal to 1, they're at a position of 44 feet off the water. And then 2 seconds later, we can see that they are -4 feet. So they've passed through the surface of the water at height 0. So they're 4 feet under the water, so to speak, after 2 seconds. Okay? And we had started this course with discussing the velocity problem as an average rate of change. Okay? So what we had here was we started looking at average rates of change, right? So we looked at this -56, for example, and we looked at this particular set of data, right? And we tried to compute the average rate of change, okay? And at around 2 seconds, we looked at the height evaluated at 2 seconds minus the height at 1.5 seconds, and then divided by the time difference, which was 0.5 seconds. And then the height change was 24 to -4, so that is a height change of 28. 28 divided by a half is 56, and that is 56 feet per second. So we were finding from this data that their position was given as a function of time, and the velocity, which is approximated by the average rate of change, can also be found from the height data. Okay, and we know that if the object gravity is 32 feet per second squared, so that's -16 t squared. This person, let's assume that they've just kind of walked off the cliff, they weren't pushed, and then at an initial height of 60 feet, that -16 t squared plus 60 is the height function. And we know now, with all of our derivative taking skills, that the derivative of this function is -32t. Okay? And if we look at the derivative at 2 seconds, the time at which they hit the water, you will get minus 64 feet per second, which is the velocity. Okay, so at each moment in the fall, we are calculating their position, what is their height as a function of time. And then at each moment, their velocity is changing, and we can see that at the moment that they hit the water, they're going about minus 64 feet per second, the minus sign indicating that they are going downward. Okay, so what we have here is a rectilinear motion problem. Right? There is only one direction of motion, and that is down in this problem because of gravity. And what we're seeing over here on the left is exactly the kind of problem we saw with the pong paddle problem. Notice that as time is changing, we can see the red dot, which is the position function. We started at 60 feet, and as time continues on, the object position is getting closer and closer to 0, which is the ground or the water. Okay, and you can see that the velocity is the black dot, that is the minus 32t. The velocity is always negative, meaning that the object is always falling downward. Okay, and then right around this time, right, if you watch this graph down here, we can see that their position, they should come into view right here at about t is equal to 1.84 seconds. We can see that their position is about 6 feet off the water. If we go 0.89, we can see that they're about 2.5 feet off the water, right? And then the closer we get, 1.96, right? They are now under the water. Okay, so we can see that the velocity is always negative. Okay, that means the object is always moving to the left, right, or down in this case. And then at some point, we reach the surface of the water at 0 height, about 2 seconds, and the velocity there is minus 64 feet per second. Okay. So this can be done again with a position and a velocity, right? If we look at this plot here and change our graph to, let's see, sine of t, we can look at a position and a velocity problem again. Let's make this sine of t. Okay, so here's our position function. And let's adjust the plot range time. Alright, let me make this a bit bigger for you so you can see. And we can compare these two. Alright, time 0. Okay, so let's take a look here. We have two different plots on the screen. We have a function called s of t. S of t will be the position of an object moving in rectilinear motion at any time. Okay, the rectilinear motion means that there's only a left and right direction of travel, or an up and down. Okay, so we're looking at the sine of t function. Okay, and we could create some data for that for the s of t function. Okay. There is also a velocity function, and velocity is the derivative, reinterpreting the derivative, which will be cosine of t in this case. So we're seeing a sine graph and the velocity graph, the cosine graph here. Okay, so here's your velocity, and this curve here is the position. Okay, now at time t is equal to 0, okay, at time t is equal to 0, we are at a position of sine of 0, which is 0, and the velocity will be cosine of 0, which is equal to 1. So that's why we're seeing the red dot here, the position is 0, and the velocity is equal to 1. Now the fact that the velocity is a positive number indicates that at this particular position, at position 0, our object is going to be moving to the right at, say, 1 meter per second or something. Okay? Now, as time moves on, let's say time gets to pi over 2 seconds. Okay? The sine at pi over 2 is equal to 1. Okay, here we are. Sine of pi over 2 is equal to 1. Okay, and the velocity cosine of pi over 2 is equal to 0 right here. Okay, this indicates that we have moved from our initial position, we have moved to, after t equals pi over 2 seconds, so about 1.5 seconds, we're at a position of 1. So the dot has moved to here, and our velocity is 0 there. So we've come to a stop at that point. Okay, when t is equal to pi, okay, when t is equal to pi, so about 3.14, the position is sine of pi is equal to 0 again, and the velocity is the cosine of pi, which is -1. Okay, so after at t is equal to pi seconds, we are back here at the position 0, but our velocity is negative, which means that we are traveling back to the left. So this object, through this particular moment, these 3 moments of time, we started here, we traveled to the right, and then we reached a stop, and then we traveled back to the left, and we keep going like this according to this position function, back and forth and back and forth. And we can see that played out, hopefully, in this. Let me show this graph. Let me recompile this graph for us. Okay. Oh, Tmax. I need to change this to about 6. Okay, so we should be able to see this plot happen. So watch the red dot down below. Okay, as time increases, okay, the velocity is a positive number, so we're traveling to the right, and we reach our maximum, and we come to a stop right here. Now the velocity is going to go negative, so the dot is going to go back to the left, and we reach a maximum to the leftward position right here. The velocity is 0, so we came to a stop. The velocity will go positive, and we're going back to the right. And that back and forth keeps happening. Okay, so that is position and velocity illustrated with just some data, and in the next videos we'll do more mathy examples.